hut 1, hut 1, hut 2, hut 3, hut 5, hut 8, hut 13, hike!
Edgar and Chives, the calculus guys.
Calculus guys.
Edgar and Chives. Edgar and Chives. Calculus rules. Edgar and Chives, the calculus guys.
Derivatives show a function's slope.
Edgar and Chives, the calculus guys. Hello, Edgar.
Hello, Chives.
We are Edgar and
The
Chives.
calculus guys.
And today we're going to talk to you about a fine lad that I like to call Fibonacci.
But Fibonacci was not his real name now, was it, Mr. Chives?
His name was not Fibonacci, it was Leonardo of Pisa.
Of pizza, you say?
Not to be confused with pizza, Pisa.
Okay, let's learn about Mr. Pizza.
Here in front of you, you see the basic mathematical functions of mathematics today. You see multiplication, division, addition and subtraction symbols, and the numbers 0 through 9. These are the most basic, fundamental part of mathematics, and they were introduced to Europe by Fibonacci himself. And the number 0 in particular, that symbol for the idea and the concept of 0, that symbol was made by Fibonacci himself when he introduced these things. Fibonacci wrote his famous book called the Liberace, and that is spelled Liberace. And this book contained all the information we were talking about earlier. The Hindu-Arabic system of mathematics, which is what you know today. And before that, in Europe, they used Roman numerals to do all their counting. Only advanced mathematicians used the Hindu-Arabic system. And then, when he came out with this book, the Liberace, and everyone could see all the information that was presented to them and how much easier it was to use, they moved to the Hindu-Arabic system of mathematics in Europe. Once Fibonacci released the Liberace to the public, it changed the course of history, not only for Europe, but the rest of the world, because Europe was the center of everything at that time, and the center of growth for science and mathematics. So once this new system was introduced to everybody, tradesmen, businessmen, common people on the streets, they were now able to do mathematics much easier, and it made everything more simple, using algorithms and all the such. And now, without those changes from the Liberace, the world would not be the same.
I'm sure many of you have heard of Fibonacci's sequence. It goes 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. Each number is a sum of the previous two numbers. But why? What does it mean? Well, Fibonacci used this sequence to answer a question. That question was, if we place a pair of rabbits in an enclosed area, how many rabbits would be born, assuming the rabbits reproduce every 1 month, and that it takes 2 months for rabbits to reach the age at which they can reproduce. This problem proves to be difficult because you have to take into account the maturation of the rabbits. Now, if it was an asexual being, such as the amoeba, you just start with one organism and split into 2, and then into 4, and 8, 16, and so on. It's modeled by this equation here. Well, thanks to the lovely magic of cinematography, we now find ourselves outside in this beautiful June weather. And I'm going to talk to you about the Fibonacci family of the rabbits. For the first month, all we have is one pair of immature rabbits. So the first generation is just one pair of rabbits. Then the second month, that immature pair now becomes mature. We still only have that one pair though, because they have not been able to reproduce yet. Then we come to the third month, which is the first month a new pair of rabbits is born. That pair that started as immature, then became mature, is now able to reproduce. So in the third month, they create a new pair of rabbits. So we have two pairs, the original pair and their new offspring. Then we move on to month number 4. That original pair has another set of offspring. So there's the original pair, their new offspring, and the offspring from the generation before went from immature, now they are mature, so that is 3 pairs of rabbits. On to the 5th month, we have the original pair, and they have a new set of offspring every month. They will keep reproducing for as long as they live, so every month there is a new pair from them. Then we have the pair that was born last month. That pair now becomes mature. And the pair that was just become mature the last month is now ready to reproduce. They have offspring. So that is a total of 5 rabbits. You can see how the Fibonacci sequence is in play here. It started with 1, 1, 2, 3, now we are at 5. And this will keep happening for every month. It will be the next Fibonacci number, 8, 13, and so on. And you can see how the Fibonacci sequence is used to answer this question about the rabbits.
Did you know that? Indeterminate analysis is when you have equations and you do variables, so there's more than one solution. Now you know! Here in front of you, we have a perfect example of what Fibonacci named and worked with the idea of indeterminate analysis. Now, there are solutions to this set of equations here, but because there are 3 variables and 2 equations, so that means more variables than there are equations, there is no one single solution.
Now we're going to take a look at the chalkboard, easel
your head's cut
of
off.
mathematics.
Where's your head?
Here are the first 5 numbers of the Fibonacci sequence, and below them are 4 more numbers from deeper in the sequence, just so you get an idea of what's going on. Now, one property of the sequence is that when you divide one number by the number before it, that division goes to a number as you move along the sequence. 1 divided by 1 is of course 1. 2 divided by 1 is 2. 3 divided by 2 is 1.5. And 5 divided by 3 is 1.66, or 1 2/3. Now if we jump down further into the sequence, 21 divided by 13 is 1.615. 34 divided by 21 is 1.619. And 55 divided by 34 is 1.617. As you go further and further into the sequence, this number approaches a number represented by the Greek symbol phi, which is 1.61803, known as the golden ratio. You recognize these numbers? Well, you should. They're the first 7 numbers of Fibonacci's sequence. And if you put them together into squares next to each other, that number would be the length of one of the sides. So 1 and 1, that makes 2. 1 and 2 would make 3. 2 and 3 gives you 5. 5 and 3 is 8. 5 and 8 is 13. It all makes sense. Now when you connect the corners of these, you get what's called the Fibonacci spiral. Now this spiral is actually seen many times in nature.
Oh, sorry.
Now over here is a lovely example of Fibonacci sequence in nature. If you look at these beautiful orange flowers, each one has 5 petals around the edge. And 5, of course, is a Fibonacci number.
Here we see another great example of Fibonacci's number in nature. 5 petals right there.
This flower is yet another example of Fibonacci's sequence in nature. 3 sets of 3 petals makes a beautiful flower.
Fibonacci sequence is everywhere!
And that is one of the things that makes Fibonacci's sequence so amazing.
Want to see a magic trick? Here are some equations. And today, I'm going to talk to you about these equations because they're related to a concept that Fibonacci called congruums. Now, congruums are not fully understood, but I'll tell you the gist of what we do now. So, if you have these equations, x squared plus h equals z squared, and x squared minus h equals y squared, what this means is that you have a square number plus something equals another square number, and that same number squared minus that same number equals another perfect square. Now what Fibonacci wanted to do is to find integers to the integer solutions for these equations, so whole number solutions. And supposedly he came up with solutions, but we don't know how he got there.
Cheeky bugger.
So that is what we do know about congruums. Alright, here we are in our trip to the past. We got Edgar over here, from the year about 1100, approximately right before Fibonacci. Now, Edgar, could you please write the number 36?
Why, of course, Chives. $36, just like you asked.
Not too complicated, a bit too long. But now, Edgar, could you please add 4? Could you put 4 onto the number already there?
Oh, of course.
But now with the new information that we know because of Fibonacci, we don't have to be quite as daft as Edgar over here. We can simply write 36 plus 4 equals 50. Now isn't that simple? Here we are on tea time, where we're going to do a quick recap. We learned about our friend Leonardo Pisano, otherwise known as Leonardo of Pisa.
Otherwise known as Fibonacci.
Indeed. And Fibonacci came from Pisa, Italy, hence his name. Now this man, he wrote a book called the Liberace. And this book introduced the Hindu-Arabic system of mathematics from Asia and brought it over to Europe because it was a much easier system to use.
Yes, this system, of course, is, you know, the 1s and the 2s and the 3s, addition, subtraction, multiplication, division,
The who's me nots,
the what have yous.
and so on. And now he did some other work as well. He got indeterminate analysis, where you have more variables than you do equations, so there's more than one solution.
And of course, who could forget the Fibonacci sequence? It has so many practical uses and very cool little pieces of it. I mean, take two numbers, add them together, and you get the number that follows. Divide one number by the number before it, and you approach the golden ratio. Take two numbers, make them squares, and put them next to each other. You keep going around, and you get the Fibonacci spiral, which is seen so commonly in nature. There's just so many practical uses.
I couldn't have said it better myself.
Now, I don't know. I really don't know.
We're gonna see you all later. It's been a pleasure.
It has. It really has been a pleasure.
Now, I'm sure AP Calculus students, you're watching this now, and you're thinking, where do I get more Edgar and Chives?
Well, we have a website.
We do not have a website. We do have a YouTube account.
We do.
Filled with some other things, but just don't worry about it.
No. But,
So go to our YouTube account,
indeed.
and eventually you might see another video.
Maybe.
Maybe.
A reunion of Edgar and Chives.
Maybe.
Edgar and Chives. College edition.
The calculus guys in college, in university.
Oh, yes! In university.
So, until next time,
Edgar and Chives signing off.
the calculus guys.
I didn't want to throw it because I don't want to knock over the camera. Now, if you put a peppermint stick in a flashlight, does nothing.
This is Chives here for Edgar and Chives, and we're going to find the terminal velocity of a human on rollerblade. Here we go. I like Fibonacci as much as I like playing basketball. From Downton Abbey!
From Downton Abbey!